Hi, my name is Anna and this is my lab report for lab number 1 on constant velocity and motion. The purpose of this lab is to analyze an object, in this case a perfume bottle that is moving at quote-unquote constant velocity, and then we will compare its predicted position to its actually observed position through the use of a computational model. And as you can see in the table of contents, all of this will be further explained. First off, there are two main theorems that need to be taken into consideration for this lab: Newton's first and second law. Newton's second law can be seen in the format of this fundamental formula that depicts F net being set equal to a change in momentum over a change in time. And this equation is easily the most important in the lab because from this you can derive the velocity update and the position update formula, both of which can be seen to the right. And these formulas do as their names show. The position update formula predicts the new position of an object, while the velocity update formula predicts the new velocity of an object. However, in this situation, the velocity update formula is not as important because the net force being applied to the system is zero, as we assume that the system is undergoing constant velocity. And this is taken from Newton's first law, which states that an object in motion will remain in motion unless acted upon by an unbalanced force. After understanding more about the physics behind this lab, the next part is to collect the observational data points, which was done through the use of Tracker. In this situation, the system would be the perfume bottle, and the surroundings would be the table, the air, and the earth. And to the right is the video of the perfume bottle that is rolling across the wooden table. And to assume constant velocity in this lab, for only frames 20 through 57 were used, as during those frames the hand is no longer applying force to the perfume. And then we plotted each position point by hand per frame and then copy and pasted the data into Google Sheets. Next, the predicted data was created and collected through the usage of GlowScript and the starter code provided. As seen in the image to the right, the perfume's original position vector, velocity vector, range of time for the time loop, and net force were all edited to fit the conditions of my lab. For the initial conditions, the ball is assumed to start the vector in the x component of 0.002963 meters, with initial velocity in the x vector of approximately negative 1.0989 meters per second. As this data was taken and were calculated from using the first 2 points of the observed dataset that we acquired on the previous slide using Tracker. And so how the code works is, first the code calculates the quote-unquote new velocity of the perfume bottle. Next, the computer uses the velocity to then calculate the updated position of the object, given that around 0.01 seconds have passed. And finally, it'll advance the clock to the new starting time by adding another 0.01 seconds before restarting the loop again. And this calculation was then repeated a multitude of times until it reached around t equals 1.234 seconds. And this is the time length of the actual video. And once I was able to consolidate the data from both Tracker and GlowScript, I was able to create this graph on Google Sheets. As indicated by the graph, my predicted positions for the perfume bottle were fairly accurate when compared to the observed data points. That means that computational models can be fairly accurate when predicting the future positions of objects that are assumed to be in a constant motion. However, it is important to note that there was less consistency in the observed data points, and this could be due to one of many reasons. First off, human error. The observed data points were done manually by hand using Tracker's data point plotter, and thus it's unlikely that the exact center of the perfume bottle was selected for every time interval. Additionally, the path of the perfume bottle was not entirely straight but moved slightly diagonal, and this could be why at certain points on the graph the predicted position was either slightly lower or slightly higher than the actually observed data points. In this next slide, we'll discuss the what-ifs, and the question for this lab is, what if the x or y axis were flipped? As seen in the center, the original line for the experiment goes in a downwards direction to the right, but if the x-axis were flipped, then this line would be flipped across the y-axis and now goes in a downwards direction to the left. Similarly, if the y-axis were flipped, then the line would be reflected across the x-axis, and the new line would go in an upwards direction to the right. And finally, we've made it to the end of the what does it mean slide. Are we allowed to assume that net force in this experiment is zero? And if so, how do we know that all of the pushes and pulls that are acting on the system? And the answer is we don't really know. For the experiment, we did assume a zero net force. However, in reality, it's impossible for us to 100% determine or state exactly all of the forces that are acting on our system, like friction, drag, etc. And this is why computational models are so important, because it allows for the creations of said systems and their surroundings where all of the forces acting on the system are selected and detailed by the creator. And that is all. Thank you for listening.